Good afternoon and welcome to today's session with Airborne Robotics and the University of Portsmouth on the subject of DrSUIT, which stands for, as we all know, the Drone Swarm for Uncrewed Inspection of Offshore Wind Turbines. We're delighted to be able to welcome Alex Ross Airfield and Dr. Victor Becerra from the University of Portsmouth and Airborne Robotics, slightly, not respectively. And I will hand over to them both now and will mute myself and stop my video once I've ensured that the presentation is sharing correctly. Can somebody let me know if that's showing up okay?
It's showing up, but not very. There it goes.
Okay, that's great.
Yeah, working. Perfect. Shall we start, Elena?
Yes, please do. Over to you.
All right. Well, thanks a lot for the introduction. My name is Alex Ross Airfield. I'm the CEO of AirSec Systems and Airborne Robotics. With DrSUIT, we describe here our 25 months project, but also a solution for efficiently conducting blade inspections in your offshore environment. Next slide. Before I jump into the topic, a short overview on Airborne Robotics. We are a manufacturer of drones, originating from Austria and also the UK. We have currently 2 offices in the UK, one in London, and our test and equipment facility in Basingstoke. And we have a manufacturing site in Austria. We develop and manufacture drones since 2014 and have a clear agenda for 2025 to achieve full drone autonomy, meaning conducting drone operations remotely from an onshore control center. Next slide, please. So going into DrSUIT, this is a consortium of 3 industry partners, starting with Airborne Robotics. We have had the pleasure to lead the project and also contribute the drone swarming technology as well as BVLOS autonomy. Then Ocean Infinity, who is the largest, or is the operator of the largest uncrewed or USV fleet worldwide. And also Bentley Walker, who stands for satellite communication in the civil and military environment, as well as the University of Portsmouth, who have contributed with 3 faculties in terms of swarm routing and scheduling, in terms of battery health management and charging autonomy, and also in terms of sensor and inspection technology. The aim of DrSUIT is to provide a full external inspection autonomy for the wind energy sector. Next slide, please. This slide addresses the need and challenge, and in particular the offshore wind farm inspection efficiency, or in that sense inefficiency. So if you look at the 2 images here, one, the infograph, which shows you that, for example, RWE offshore wind are moving more and more from onshore to offshore. We're talking about 200 kilometer far out offshore. So the distances are becoming bigger, the turbines are becoming ever larger. And if you then see the traditional method of rope hanging, teams of 2 or 3 people climbing up and down the blade and taking centimeter by centimeter recordings of the blade, you can see that this is relatively inefficient. Now, the drone as a means to remotely inspect turbines is established already in the market, that's for sure. Not so much offshore, but mainly onshore. We are going here a step further. So we are going away from the one situation, one pilot, one drone, to a fully autonomous system with multiple drones. And the challenge to overcome is to reduce costs and carbon emissions from vessel rides between onshore and the wind farm, going out and back again, but also to increase the digital footprint, to increase inspection flexibility and safety, and overcome or minimize downtime, which means a loss for the wind farm operator. Next slide, please. The concept of Dr. Soot is the following. So if you look at the middle of the chart, you see one or more USVs which will be used in operation. They house lab systems, so launch, recovery, and recharge platforms. Each of them houses at least one drone. So they are equipped with a swarm of 4 or more drones. And the drones, as well as the vessel, is connected to the onshore control center via SATCOM. The SATCOM link between the drone and the onshore command center is for navigation purposes. The one on the vessel is for data transmission and also operating the lab system. And then you have the control center onshore. The drones are organized in strands. So while 4 drones are in operation, 1 or 2 for each strand are charging, so that we can permanently operate the Dr. Soot system. And the operators in the control center can step in if required, but generally the operations are done autonomously. Next slide, please. Here I would like to hand over to Victor, who will talk you through the project work packages. One thing should be remarked here. We do not display the fully up-to-date status of the project. That's due to the confidentiality. But it gives you a fairly good overview of what we're working on and where we are at the moment. Thanks, Victor.
Thank you, Alex. Yes, this project ran over a period of 25 months from March 2021 until March 2023. The work was divided into 5 work packages. We have illustrations here on the slide about the different work packages. So work package 1 involved developing technologies for a 5G and satellite-connected drone swarm. This involved establishing connectivity and communications between the drones and an autonomous barge using 5G, which was essentially local communication, as well as data and video connectivity between the barge and a control center, a remote control center using satellite communications. We also have work package 2, which involved developing a 5G and satellite-connected battery health management system that is able to accurately estimate and predict critical parameters of the drone battery, including, for instance, the state of charge and the state of health of the battery, as well as predicting the remaining battery life. It also involved the development of an autonomous charging platform for the drones, which is illustrated on the image here. Work package 3 involved algorithms for real-time optimal scheduling and routing to plan and manage the operation of autonomous vessels and drones. There is a couple of separate slides on this topic in a minute. We have also work package 4 that involved experimenting with sensor technology to detect and monitor surface and internal damage on turbine blades using sensors such as high resolution RGB cameras, hyperspectral cameras, as well as immune tomography sensors, which use cosmic rays to gather information about the internal structure of materials. Work package 5 involved the demonstration of a systems use case. There are a few videos later on in this presentation that will illustrate aspects of this demonstration. Next slide, please. So as part of the project, we produced a number of outputs, publications. Some of them are illustrated on this slide. They were presented in conferences, and we are happy to provide copies of digital copies of this, links to download these publications upon request. Illustrated here on the slide is a publication on the scheduling and routing algorithm. Then there is another publication on experimental work on sensor technology, in which various sensors were used to detect a range of different types of faults on the blades. And then another paper on the intelligent battery management system that was developed as part of the project. Next slide, please. This slide illustrates the work on optimal drone swarm route and vessel routing and scheduling that ensure the optimal routing and scheduling of both the vessel and the drones, in order to maximize efficiency and also to reduce downtime of the wind farm. The drones work collaboratively and adapt autonomously to real-time data, and then their operation is rescheduled and pre-planned according to a range of circumstances, including the weather. There are, as part of the model, there are power supply and energy consumption constraints, weather conditions, different payloads, and so on. All this is considered in the model. The model also provides an optimal fleet composition for each inspection task. For example, it determines the size of the inspection window and the number of autonomous vessels, as well as drones that are required, depending on the characteristics of the site to be inspected. There is also full integration of these algorithms with the swarm software that is part of the software suite used by and developed by the company, AIRBORNE Robotics. Alex, you are in charge of the next slide.
Yeah, next slide, please. Okay, so what we show here is an offshore wind farm. It's one of the biggest wind farms in the world, Gwyntimore, in the north of Wales, with 160 turbines and 600 megawatt output. You can see here in the middle, in the larger chart, so what it's flipping around here. Can we go back to yeah? Okay, so what you can see in the middle is we have used here as an example 4 vessels, and so in the middle the wind farm with the exact positions of the turbines. You see on the right side a smaller chart which shows you the halting points and the route that the 4 vessels are taking. So green is, for example, vessel 1, brown is vessel 2, and so forth. And you have about 9 to 11 halting points per vessel. And with this route, which is optimized, we would be able to inspect the entire wind farm of 160 turbines in 1 day. So the total outcome is 525 minutes. So what happens is that each of the vessels moves from one halting point to the next. 4 drones swarm out, do the inspection, come back to the vessel, and then again the vessels move to the next halting point, and again 4 drones would swarm out. We can go to the next slide, Ellen. On the innovation side of things, here to mention the vessel itself. So the first vessel, which was commissioned in 2021, 2022, has been built. It was the first of 4, and there should be also a short video. I'm not sure if we can show it, Helena. Do you think you can show the video, Elena, or is it not working? Yeah, it doesn't matter. So basically, the vessels they can be manned or crewed, and they can be also uncrewed. Ultimately, they should be uncrewed at the end. And they accommodate the lab systems, typically 4 or 6 such lab systems. The vessel is operated from the onshore control center, which is in Southampton. So there is a control center for the vessel, but there's also a control center to operate the drone fleet. We can go to the next slide, please. Part of the vessel equipment are the lab systems. So while it's not the latest design, it shows you quite good what it would look like. So it's a containerized system with maritime grade characteristics. And it has it houses space for multiple drones. So in that case here, up to 4 drones. We would need 2 to 3 drones per strand, so that we can provide uninterrupted flying throughout the whole inspection tour in the offshore farm. Of course, the lab system is connected via satcom to the onshore command center, and it can be operated remotely from that command center. Next slide, please. Going on with the innovations. So drone autonomy is quite a big topic here, and it consists of dynamic ship landing, but also of collision avoidance or flying in GPS-denied situations. So most importantly, the ship landing, which is something which is not as straightforward as someone might think, because the vessel drifts. So we see in the first image here the ship heading 90-degree east when the drone starts, and after 15 minutes, when the drone comes back to the vessel vessel might have shifted. So in the second case, you see the vessel facing you're heading probably 100 degrees south. So while the vessel moved, the drone needs to find its home point, and that's done through the support of a maritime grade GNSS, which tracks the exact position and the rotation of the home point, so that the drone can come back to its altered home point. And we have tested the system over months in order to track the performance, and we were quite surprised and quite, let's say, pleased how good the performance is here. On the other hand, the other component, collision avoidance, we have our proprietary vision system. So the drones are equipped with GPS, but also a vision-based navigation system so that they can fly in GPS denied, and also in order to have collision avoidance. Next slide, please. Another part of the innovation work packages is comms, the comms part. So here you can see at our Basingstoke facility, satcom terminals on the roof of the building. We have tested also here a system from OneWeb over months in order to test the reliability, stability, and the data throughput. And again, here, really good performance with very low latency. So we're talking about 100 to 200 milliseconds, which is fantastic, and bandwidth of 75 megabits per second. So this is really more bandwidth than we would need, and it gives us an independence anywhere in the world where there's no 4G or 5G, in order to have connectivity to the lab system and to the drones. Next slide, please. Very important for the overall work is also simulation. So why is it so important? Because when you want to test certain aspects, it would be quite costly to go out to the offshore wind farm all the time. So what we have done, we have created a simulation environment in order to test any technical aspect, but also the operational aspect. So it is a digital twin for all technical features, but also for to demonstrate operational preparedness, to demonstrate also what is happening through the operations. And it supports, of course, also risk assessment and preparations for example, for the CAA and also for the operators to sign off on the operation. Elena, would you start the video, please? So typically we would have a sound here. Doesn't seem to work in the webinar, but what you see is the ship arrives at the holding point and 4 drones swarm out. We see now we follow now 1 drone, that's drone number 2. You see the distance from the vessel, the distance to the turbine, the flight duration, in that case 5 minutes so far. The speed, the typical ascending speed is about 2 to 3 meters per second, and the drone takes permanent images, GSD of 0.5 to 1 millimeter, and that from a safe distance of 20 meters. So once the mission is completed, the drones come back to the vessel, land on the vessel, and then move, and then the vessel can move to the next halting point, so that again they can start from there. Next slide, please. Yeah, that's the one. So what we focused on during the project is really on the let's say, the point between the vessel and the onshore control center. I've mentioned it already before. The actual inspection of wind turbines via drones as an innovation is not new. So that's it's an accepted system, and I would say in many larger industry groups or operators, the inspection of drones of wind turbines has moved from the innovation department to the procurement department. So there's an established market for that. But what we are focusing on is here, how can you scale that? How can you make it more efficient, and how can you make it more efficient from the time span and also more secure? And so what we have done here is we have conducted a set of trials with 4 drones, and we are talking about our heavier lifter drones. So those are small drones. Those are drones which can mount up to 10 kilos. And what you see here is the vessel with the drones on deck, 4 drones. And you see also our control center in London. And what we will show in a video in a few minutes is that the drones are operated from the control center, of course, in an environment which is secured. So we have pilots on board who can step in all the time. And so these parts, we focus on these parts which are very important to give ultimately a reliable operation for Dr. Sood. Next slide, please. And we can start the video. So again, we don't have a sound, but what you can see is, so the pilots on the vessel are preparing the drones, which are then operated from the control center. So you can see how they lift off. We have, just for demonstration purposes, conducted some kind of swarm formation here. Yeah, it's slightly difficult without any sound to get excited about that video. The link is actually here listed on the bottom. So if you want to see the original video, that can be easily done. So we are flying some swarm formations and then come back, land on the vessel again. So next slide. Yeah, that's it for the presentation. We're happy to answer any questions you have now. Yeah, thank you, Elena, for doing the slides.
Apologies there for the lack of sound. I will ensure that when we send it out as watch again link, that everyone receives the proper links as well. I'm not sure why that happens. I think YouTube and Zoom don't like talking to each other. However, in good news, we have plenty of time for questions, and we have our first couple up here as well. Please do add them to the Q&A section, and we'll be delighted to answer them. So first question up is, blade manufacturers are already using fiber optic to monitor blade shear stress and integrating sensors to monitor lightning protection earthing. To what extent are you liaising with them to understand how best to optimize sensor design?
So we are not here to design sensors for blades and for the offshore wind operators, but what is for sure that multiple routes are taken in order to make sure that the condition of the blades is held upright all the time. So there are sensors which are fixed to the turbine or to the tower, etc. And there's of course also remote inspections and inspections from rope hanging teams. So all of that comes together, and using drones is fairly new, but it is established for wind turbines, and what we are trying to bridge, some of those let's say challenges which are out there. We cannot cover all of them. Of course, we cannot do any inspection from internal, so internal inspections. That's not possible. So we're trying to cover the what we think is a little bit of a bottleneck is the blade inspection, which is currently done manned and relatively, let's say, in an environment which is harsh and dangerous. But of course, if there are sensors out there, and we know for sure that they are, they might cover different angles from what we couldn't do from the drones, and the combination of it makes it, and that's what the offshore wind farm operators are looking for.
That's great, thank you. Our next question is, allowing for certification / Lloyd's registration for your uncrewed vessel, how long before you have a minimum viable product ready for market sale?
Yeah, so I cannot speak for the uncrewed vessel. That's Ocean Infinity, and they are masters in what they are doing. That's for sure a process which is probably a few years into the future. The important thing is here that the vessel can operate like it is now, crewed, can be uncrewed, and so in general there's going to be a transition time, I would assume, where there is some semi-autonomy until we get full autonomy. It's very much like in, I can only speak for the drone side of things, and here it's also a phased and stepwise approach. Yeah, I don't know, Victor, do you have anything to add to that?
Not really, no. But yeah, as everything, this is critical infrastructure which is being inspected using vessels on drones that exhibit some sort of autonomy. Clearly, there are steps that need to be taken in order to have the necessary approvals. But yeah, I think all organizations involved, all commercial organizations involved, are making progress, both with the drones and with the vessels.
Thank you. Our next question is, have you consulted with wind farm operators? Are they in favour of stopping all turbines on one day to get all inspections done?
Yes, of course we did. And it's not the aim to stop all the turbines for an entire day. So first of all, Dr. Sood addresses the more, let's say, the newer generation of offshore wind farms. So the ones which can be remotely stopped, halted, and also turned on again. So that's the aim. We would not expect the offshore wind farm operator to stop the turbines, all turbines for one day. That wouldn't make sense. But I think it's a very relevant question, and I'm happy that you brought this up.
I was funnily enough, I was going to ask in how long do they get, given the newer turbines, how long do they get switched off for at a time while you're doing this? I assume it's sort of each leg. Can you turn sort of 20 off at a time while you're surveying those ones?
So we would need for the entire inspection of all three blades from 4 sides, we would approximately need 12 minutes. Yeah? So be 12 or 15 minutes, it doesn't really matter, but this is more or less the time frame. So we're looking at maybe a window of 30 minutes, and it then depends on what kind of how fast the offshore farm operator can react and turn it on and turn it off. So, but we for us need not more than 30 minutes.
That's really interesting. Have you undertaken any cost benefit analysis to the customer, i.e. by using your system in development, they will make indicative savings of X pounds against current methodologies?
Yes, of course we've done, so we can reduce the cost massively. So our initial calculations are that we can reduce them by 90%, up to 90%, I would say. And then, I mean, obviously, there's always costs involved, which we don't know at this stage, but the cost reduction would be somewhere between 50 and 90%.
That's really quite large. And in terms of health and safety savings as well, in not putting people at risk in dangerous environments, that also must be a considerable saving for any company and wanting to undertake this.
Yes, absolutely. That's one of the major points, and one of the trigger points actually for the project, because that was one of the things that was mentioned, let's say, as one of the first points, and we know it for sure also, that even if you use drones on a vessel, it is already quite efficient when there's a pilot standing on the vessel deck and operating a drone. But still, that is quite dangerous, and still that is quite uncomfortable, or could be uncomfortable. Being out on the sea, when it's rough, when the weather is kind of not the most pleasant one. So there's a lot of things which go in the direction of health and safety, of course, but other things as well, like we've mentioned the carbon footprint. We've mentioned for each turbine currently, a transfer vessel has to go out on the come from the harbor out to the offshore wind farm. It's typically it's not a small crew which is involved in that, and the output obviously is a fraction of what we can do when we have 4 drones in operation in one day.
It is absolutely fascinating. How, in terms of sort of the health and safety savings, how is that quantified? Do they quantify it even?
Victor, would you like to do this question?
Yes, yeah, I think essentially one way, I mean, the most serious risks are associated with the personnel that climbs the tower and onto the blades in order to inspect them. using drones, this phase of the inspection is completely eliminated. So in that case, it will be 100% reduction of that risk. If you see what I mean, because you are using a drone, and no longer it is necessary for a person to climb the tower or the blades to do the inspection. But yeah, there are ways of quantifying the different benefits. For example, it is possible also to quantify the reduction in emissions. There is also the fact that the drone-based inspections are less sensitive to sea and weather conditions. So there may be levels of weather conditions where the crews can no longer operate, whereas the drones can still operate. And again, this increases the benefits because you can inspect, you have more possibilities of actually doing the inspections.
Just to add, Elena here, so to give an example, the moving from the vessel to the turbine is extremely dangerous. Yeah? So you don't even have to be on the blade yet. You don't even have to be on the top of the tower, but only the phase where the crew moves from the vessel to the first and second platform. So this is extremely dangerous, and all of that, of course, can be neglected if you can remotely operate drones and there's no human involved in that situation. So I think the benefit in terms of health and safety is extreme here as well. Yeah.
Absolutely. It is. I think it's absolutely remarkable. How satisfactory is the use of UAS for offshore surveying and remote energy assets inspection?
So it would have to be clarified a bit better what offshore surveying would be. So energy asset inspection, I mean, we have that's our core topic. Yeah. So what we provide would be high resolution images, everything in digital form, and that remotely. So a remote inspection is a remote inspection. So that means that there is obviously no physical interaction with the actual blade. So I think that's maybe one of the differences between having manned inspection. So you can obviously touch and feel the surface of the blade. So remotely done, it gives you high resolution images. It gives you all they are stored, and it gives you all the evidence and so on. But there might be a slight difference. So when we in our discussions with operators, there are certain requirements, and they are met by far in terms of the resolution of the images. So in that respect, we can surpass the let's say requirements. So if there is 1 millimeter GSD or 1 millimeter per pixel required, then we can get 0.5 of it. So that's, I think it should be very satisfactory.
That's great. Has your engagement with the CAA on offshore BVLOS swarm operations been positive? Do they or you foresee any significant barriers to approving these operations?
So the regulatory question, of course, is always quite a big topic. Yeah? We are still at the moment in the development phase. So our aim is to be ready with the product in 2025. So our situation is currently still considered as a development. And what we have learned is, and we were part of the Future Flight competition and initiative. So what we have learned is that the CAA, as well as other national authorities across Europe, are very open to let's say, interesting use cases and supporting these interesting use cases in order also to learn more and also to collect data, to collect test data, etc. So that's it's a mutual process. Most of the use cases are not only new for the drone operator or in terms of the project, but they are also new for the CAA. And so it's a kind of for us it's a positive process. We can only expect things to be approved where we have kind of risk assessment in place, where we have got mitigation plans. But we have our approach was always very positive when talking to national airspace authorities.
Right, I'm very pleased to hear that. What is the wind speed limit for the drones to fly so close to the turbines?
Yeah, that's a question we hear quite often. Look, it is hard to really nail that down, but I think everything above 25 kilometers per hour wind speed is getting difficult. But with Dr. Soot, we are intending to, let's say, we're intending to go further away from the blades as it would be normally seen. Yeah? So we are we have at least 20 meters, and hopefully in future this will be possible to be even more than this 20 meters. So we are certainly aware that this is one of the most critical things. How do I get a safety distance but still have the granularity of the information and data that is required? So for now we are happy with 20 meters, and I think in future sensors will become better and better, as probably everyone knows. And so we are quite positive in that sense on that topic.
Excellent, thank you. I think my final question was going to be, and this one from me personally, which was that you mentioned the wind turbine field just off North Wales of being a total number of 160 wind turbines, and that you're able to inspect those all within 1 day. How long did it take pre-drones to inspect all of those? Out of interest, what sort of time scales are we looking in terms of time savings?
So my understanding is that the entire inspection of one turbine takes a day of a team, let's say of 12, including crew transfer, vessel, etc. So if you have a rate of 1 day compared to 160 per day, I think that's very favorable. But even if it's only a handful of drones, a handful of towers, which you can do, I think it's already great benefit. So the margin between what is the output at the moment to what could be done, if we have one vessel or more vessels and 2 drones flying at a time or 4 drones flying at a time, I think that's massive. Yeah, and so it's also it's not only how much can we do in 1 day. It's also a system, and that's why we have developed with the University of Portsmouth together the routing and scheduling algorithm. So that's a system which can adapt to the let's say available time slots. So for example, one of the issues is the windows of opportunities to go out in the wind farm and do those inspections is fairly tight. So if you, for example, have a window of 3 days, then we can calculate. So how do we best use that 3 days? Yeah, we could take 1 vessel and 4 drones, or we take 2 vessels and I don't know, maybe 6 drones in order to get as much done as possible in that window. And that's the other side of the gain when you have a system like Dr. Suit.
Yeah, absolutely. I think the scheduling is crucial. I think it's very fascinating. And we have one final question here. Are your SAT communications direct to the drone or just to the ship? And is the ship to drone communications on standard RC radio links?
So there are various options for that. We have a direct link between the drone and the onshore control center, that's SATCOM, and we have also the link, the much larger and much larger bandwidth link from the vessel. So why do we distinguish between that? Because the drone doesn't need to transmit the data instantly. Yeah? So we don't need as much bandwidth, but we would like to have control. And if you have direct control, it's probably better because it kind of adds latency if you have a relay or so on. But the answer to your question, or let's say your question is very good, is very relevant because it picks up on a topic which we have been asking ourselves all the time. And so we are not quite through yet with all the options we have, but we are testing, well, we have been testing both direct link from the drone via SATCOM and also relayed. We have also used 5G, we have also used 4G in the loop here. So there's various options, which it is not only a question of what is the output of that option, it needs to be also in the light of what are the costs involved and how is the practicability. So 5G sounds very often very good, but in many cases it's either not available or it's maybe not practical. Yeah? So in that sense, a combination of all of them is still being tested, but both direct and relayed over the drone, over the ship are possible.
Thank you. What type of power are the Ocean Infinity vessels, electric or turbine?
Yeah, I can't answer this question, to be honest, but my understanding is they are not electric at the moment.
Okay. Thank you.
Yeah,
Do we have any further questions?
Victor, I think you had something to say on that.
Yes, I had some information on that here.
Excellent.
They are looking at using ammonia as fuel in the future. And they also currently use technologies to reduce emissions as much as possible. But this, you're right, Alex, they are not electric.
That's great. Okay. Thank you. Sorry to interrupt you there, Victor. Do we have any further questions at the moment? If not, I will close the session now. I will send this out to everyone this afternoon alongside the correct video link, so that you can see and listen to the video recordings. It's been an extremely interesting subject to talk about. I've thoroughly enjoyed it myself. It's one I've had a close eye on for a number of months, and I'm delighted that we were able to welcome Alex and Victor here today to talk about it with us. Alex and Victor, if you're happy, I will include your contact details to pass on to anybody who would like to follow up with any further questions that they might have about the subject.
Of course, no problem.
Perfect. Thank you.
That's lovely. Well, thank you very much indeed, gentlemen. Thank you very much to those two who have joined us this afternoon, and we will look forward to seeing you again shortly. Thank you very much then, everyone. Bye-bye.
Thank you. Bye.